A massive steel skyscraper exerts millions of pounds of force on the earth beneath it. For an engineer or an urban farmer, the success of a project often hinges on the chemical and physical variables hidden within a single patch of ground. Soil behaves as a chaotic matrix. It can harbor toxic elements left over from decades of industry, shift its physical properties based on trapped water, or compress unevenly the moment it's forced to carry a load. Because these behaviors are invisible from the surface, we rely on rigorous testing to interrogate the ground before we ever break it. Scientists divide this interrogation into 3 specific domains. They measure soil to protect our health, to manage our water, and to calculate its physical strength. This data turns the ground into a predictable platform, allowing us to safely inhabit and build upon the earth. In the chemical domain, the focus is often on urban safety. The Safe Urban Harvest study in Baltimore demonstrated that city soil can hold a legacy of lead and arsenic from past construction. Detecting these threats requires a representative sample. Technicians collect 10 to 12 individual scoops from a depth of about 6 inches across the site, mixing them to ensure the laboratory results reflect the entire area. In the lab, the sample is dissolved through a process called aqua regia. As shown here, intense heat and a combination of nitric and hydrochloric acids break down the soil particles. This isolates specific heavy metals so they can be identified and measured. This intense chemical digestion targets the environmentally available metals, the specific amount that could actually pose a risk to human health through contact or consumption. These tests translate an invisible hazard into clear data, allowing communities to determine exactly where it is safe to grow food. The second dimension of testing tracks the water trapped within the soil. Moisture levels determine whether a crop will survive a dry spell or if a hydroelectric dam will maintain its structural integrity. Historically, the standard was the gravimetric method, weighing a sample, drying it in an oven, and weighing it again. While accurate, the process is too slow for anyone needing a real-time update on field conditions. Engineers in the mid-20th century experimented with neutron and gamma radiation to get faster results. However, these methods were largely phased out due to the significant health risks and specialized safety protocols required for handling radioactive sources. Modern sensors now use dielectric methods like TDR and FDR. As this diagram shows, they send pulses of electromagnetic energy into the ground. By measuring how the soil's electrical properties respond, the sensors can calculate the exact concentration of water molecules across different depths. This technology gives farmers and engineers immediate, non-destructive data, allowing them to monitor the stability and health of the soil without disturbing it. The mechanical domain deals with physical limits. Before construction begins, civil engineers classify the soil by grain size to understand how it will respond to weight. Coarse materials like sand are easily sorted through sieves, but fine clays are more complex. Engineers must measure a clay's shrinkage limit to predict how much the ground will contract as it loses moisture. A wet soil pat is dried until its volume stops changing. To find its exact volume, engineers submerge the shrunken sample in mercury. A glass plate pushes the soil down, and the displaced mercury reveals its precise physical dimensions. From there, labs use triaxial shear and unconfined compression tests to simulate the pressure of a massive building, identifying the exact point where the soil will fail. Finally, the standard Proctor compaction test identifies the moisture level needed to pack the earth to its maximum dry density. This mechanical data ensures that highways stay level under traffic and skyscrapers remain stable in the silt. Through the rigorous sciences of chemistry, hydrology, and geotechnical mechanics, a chaotic natural mystery is carefully converted into precise mathematical data. That data has concrete outcomes. It tells a gardener to import clean compost. It triggers an automated irrigation system on a farm, and it provides the final approval for a building's foundation. By analyzing the ground to this level of detail, we turn soil into a reliable, engineered component of the world we've built.